Good day and welcome to my YouTube channel. I am Arthur Francis the man. Today we're going to be taking on Redox Calculations. We've dealt with volumetric analysis, which we have already treated most of these areas of the calculations. Redox is part of it. Only difference is that it deals with a net equation, half-cell equation, other than the usual kind of how do you call them, neutralization reactions where we have our salt and water. But in redox, it seems different. And another unique thing which makes it beautiful is the formula tends to take a different look. But before I talk about the formulas, redox titration deals with the oxidizing agent and the reducing agent. For example, we have the potassium tetraoxomanganate 7, potassium heptazodichromate 6, we have the iodine, we have the potassium iodide, and all of that. And many a time we use our potassium tetraoxomanganate 7. It's a strong oxidizing agent, and because of its strong nature, it tends to oxidize the substances or the compounds in which you react with. So many a time, if it is too powerful, especially when you use it with a chloride compound, which is a reducing, it oxidizes it. So in such a situation, we tend to use another, how do you call it, oxidizing agent, and we will afterward apply what we call it an indicator. Most often, redox titration is self-indicating. We only acidify the reducing agent in the course of reaction using H2SO4. But all things being equal, the calculations therein are the same in all ramifications because we can still use the redox principle to calculate for our percentage of water of crystallization, percentage purity, normal molar concentration, and mass concentration, and so on, even amount in all of that. So let's see what we can do, and then we'll move on. All right. So in the formula, like I said, in the previous, we use this formula CAVA over CBVB equals to NANB when we are treating with normal volumetric analysis calculations. But in redox, instead of using concentration of the acid, we say concentration of the oxidizing agent, volume of the oxidizing agent, concentration of the reducing agent, volume of the reducing agent, equals to the number of moles of oxidizing agent over number of moles of reducing agent. So that's what it is. Since the calculation of the titration is principally based on the oxidizing agent and the reducing agent. And quite often, the oxidizing agent, KMNO4, is often in the burette and other oxidizing agent. But there are certain times where the reducing agent, which we know, tends to be in the burette, as the question will go, as it suits them best. So we are going to take questions and see what happens. And most also, student commented that I should be writing the questions. It's good to write, but just tends to take us time and space. But then what I'm going to do now is to read the whole question, so that even if you're going through the question, by listening to the question, you can easily write it down if you want to. Then I will now bring out the variables which I've read and state them out as a given. With the variables alone, knowing that the oxidizing agent have these parameters given, the reducing agent have these parameters given, you do not need the whole question, like read it, so you can just tend to start solving them as the case may be. So let's see what we can do. First question, I will read it before I state out the given. A is a solution of potassium tetraoxomanganate 7. B is 0.02 mole per dn cube of ethane dioic acid. and solution C is 1.0 mole per dn cube of concentrated H2SO4. So the corn H2SO4 will be used to acidify the system. If 25 cm cube of solution B gives 16.5 cm cube of A for complete oxidation, from the equation of reaction below, which is given, I will state it out, we should calculate the concentration of solution A in mole per dn cube. A is the oxidizing agent. Concentration of B in GDN cube, the reducing agent. And also have the third question here, which is amount of A in the average volume of acid used. So we have done all this calculation, calculate concentration of this and that. So I mean, likely not just solving everything down. I can leave some for us to try and see what we can do. So now let's take out the given. I will write out the given. So A is a solution of KMnO4. This is A, KMnO4. A is a solution of KMnO4. B is of ethane dioic acid, H2C2O4. Yes. Now, B is 0.02 mole per dn cube. Okay, now concentration of the reducing agent is 0.02 mole per dn cube. So these are the given parameters. Okay, solution C, blah, blah, blah. If 25 of solution B, volume of the reducing agent is 25 cm cube, react with 16.5 of A, volume of the oxidizing agent is 16.5 cm cube of A for complete oxidation. From the equation of reaction, let me state the equation of reaction so I'll be able to get the number of moles of oxidizing agent, number of moles of reducing agent from the equation of reaction. Here is our equation, 2NO4 minus plus 5C2O4 minus 2 plus 16 hydrogen plus gives us 2Mn 2 plus 10 CO2 plus 8 H2O. So this is the equation of reaction. Okay. From here, this is the oxidizing agent. We have 2 moles. It's 2. Reducing agent, we have 5. Now, concentration of the oxidizing agent is what we don't know. So that is it. We've established that. So questions. A, we should calculate the concentration of solution A in mole per dn cube, which is concentration of the word oxidizing agent. So, permit me to take this equation out. We have gotten what we want, or wanted to make. So, we're looking for this. We use our formula. Concentration of oxidizing agent, volume of oxidizing agent, concentration of reducing agent, volume of reducing agent is equals to number of moles of oxidizing agent over number of moles of reducing agent. So for us to make this a subject, I have my concentration of oxidizing agent to be equals to concentration of reducing agent, volume of reducing agent, number of moles of oxidizing agent over volume of oxidizing agent and number of moles of reducing agent. And this is equals to concentration of reducing agent is 0.02 mole per dm cube. 0.02 mole per dm cube. Volume of reducing agent is 25 cm cube times number of moles of oxidizing agent. Number of moles of oxidizing agent is 2. Volume of oxidizing agent is 16.5 cm cube. That's number of moles of reducing agent, which is 5. And this is equals to, we use our calculator here, 0.02 times 25 times 2 equals to this. Divide by 16.5 divided by 5 is 0.0121. 0.0121 mole per dm cube. Okay, if we have that's our first, the second one, concentration of solution B in GDM cube. So let me put that down. Here is 0.0121 mole per dm cube. Now, concentration of B in GDM cube. In GDM cube, let me clean the board, please. Count of B in GDM cube. This is equals to this. Now, it's equals to GDM cube, which is mass concentration of the ethane dioxide, which is the reducing agent, is molar count of B times relative molecular mass of B. The molar count of B is 0.02 mole per dm cube times the relative molecular mass of this. Hydrogen is 1 times 2 is 2, plus oxygen is 12 times 2 is 24, plus, sorry, that's carbon. Oxygen is 16 times 4, which is 64. So 64 G mole. And this is equal to 0.02 mole per dm cube times 90 G mole. And this is equals to 0.02 times 90 is equals to 1.8. 1.8 GDM cube. So let's verify that A is a solution of KMNO4, B is 0.02 mole per dm cube of ethane dioxide. So we've done the needful. Now C, my C is assignment. It's for you because we've treated amount. We remember the formulas for amount. We have mass over, mass in gram over relative molecular mass in G mole. And we also have amount to be molar count times volume. So the question here is asking you to calculate the amount. C, calculate the amount of A in the average volume of A used. Amount. If you look here, you can just see the solution. So that's question number 1. Let's take our second question. Question number 2, I'll read it again. 0.02 mole per dm cube of KMnO4 react with 27.52 GDM cube of iron 2 tetraoxosulfate 6, hydrated iron 2 tetraoxosulfate 6, and 25 cm cube of the reducing agent react with 25.60 cm cube of the oxidizing agent. If the equation of reaction is this, we should calculate the number of moles of water of crystallization in iron sulfate, iron 2 sulfate, and calculate the percentage of water of crystallization B. C, calculate the percentage of iron 2 in iron 2 tetraoxosulfate 6, I think heptahydrate. So which means they are giving us a clue that our final answer is supposed to be a heptahydrate. Now let's state out the given. KMnO4 is A. Okay, let's just call it here. KMnO4. This is 0.02 mole per dm cube. Concentration of oxidizing agent is 0.02 mole per dm cube. React with 27.52 GDM cube of iron 2 tetraoxosulfate 6 hydrate. Okay. React with 27.52 GDM cube. Okay. This is the GDM cube of the hydrated salt. Thereabout is 27.52 GDM cube. And 25 of the reducing agent, volume of reducing agent is 25 cm cube. Let's say react with 25.6. Volume of oxidizing agent is 25.6 cm cube. If the equation of reaction is given to be this, so we are using that to get our number of moles of oxidizing agent, number of moles of reducing agent. Okay, now this is our equation of reaction now. We have MnO4 minus plus 5 iron 2 plus 8 hydrogen plus gives us Mn2 plus 5 iron 3 plus 4 moles of water. Okay, from the equation of reaction, we know our number of moles of oxidizing agent is 1, and number of moles of reducing agent is 5. From there, they say we should calculate the number of moles of water of crystallization in iron 2 tetraoxosulfate 6. So this is a not very direct question, because I think we've not gotten a lot of the parameters required or they didn't give us. So they are just asking us straight up to get what they want us to get. But I think there are a lot of other things we have to do before we get there. So let's look at the question again. We have concentration of the acid, of the oxidizing agent. We do not have concentration of the reducing agent. And they are asking us for percentage of water of crystallization, which means that we have to get, they've given us the mass count of the hydrated. We have to get the mass count of the anhydrous, which is just this. When we get the mass count of the anhydrous, before you get it, you need to get the molar concentration of the reducing agent, which will help you to get the mass count of the anhydrous. See, that's the technicality. So we must have to know our concentration of the reducing agent. That's what we get before the mass count of anhydrous, which we don't know. So let's start with this first. For us to do that, I have to write out our equation. Please let me take this guy out. I have concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent is equal to number of moles of oxidizing agent over number of moles of reducing agent. I'm looking for concentration of reducing agent. So my concentration of reducing agent is equal to concentration of oxidizing agent times volume of oxidizing agent times number of moles of reducing agent over volume of reducing agent times number of moles of oxidizing agent. And this is equal to concentration of oxidizing agent is given to be 0.02 mole per dm cube times volume of oxidizing agent is 25.6 cm cube times number of moles of reducing agent is 5 over volume of reducing agent is volume is 25 cm cube times number of moles of oxidizing agent is 1, and this is equals to, let's use our calculator. We have 0.02 times 25.6 times 5 is equals to this divided by 25. We have 0.102 mole per dm cube. Okay, so concentration of reducing agent is 0.102 mole per dm cube. If we have gotten this, now I have to calculate for the mass concentration of the anhydrous. Mass concentration is molar count times relative molecular mass, which means I'll be looking for the relative molecular mass of this. I know why I'm doing that, because the formula says relative molecular mass of hydrated over mass count of hydrated is equal to relative molecular mass of anhydrous over mass count of anhydrous, as the case may be. So now let us get the mass count of the anhydrous. I claim this. Now, mass count of the anhydrous salt, anhydrous reducing agent, is equal to the molar count of that times relative molecular mass. The molar count is given to be 0.102 mole per dm cube. The relative molecular mass of this ion should be 56, if I am not mistaken. Okay, number 2, ion. I didn't state it, but I think it's 56. Let's go on. So we call it 56 plus sulfur is 32 plus oxygen is 60 times 4, which is 64. Okay. Now let me add that. 56 plus 32 plus 64 is equal to 152 times 0.102, 15.5. Okay, this is 15.5. All right, 5 GDM cube of anhydrous. Okay, normally in almost every question, when your that gives you this element or compound, that give you the atomic masses so that you'll be able to determine your relative molecular mass. But probably I forgot, I didn't take note of that, and we have to move on. All right, what again? We have gotten this. Let me clean. Now, we have gotten, they are asking us for the number of moles of water of crystallization, which is the X. Yeah, we want to know what is the number of X. Is it decahydrate 10, pentahydrate 5, heptahydrate 7, and so on? That's what we're looking for. So let's get to it. All right, let me clean this. I've gotten that value. Did I put it up there? GDMQ of anhydrous is 15.5. 15.5 GDMQ. Now, I can take out this. Now, to get our X, we say, the formula says for number of moles of water of crystallization says relative molecular mass of hydrated, let me just shorten it that way, over mass con of hydrated, relative molecular mass of anhydrous, mass con of anhydrous. Now, what is the relative molecular mass of the hydrated? Oh, relative molecular mass, which is this. I calculated it to be 150 something, 152. Yeah, I think so, 152. Let me start again. 64 plus 32 plus 56. 152. Okay, that's the relative molecular mass of this plus this phenomenon. So relative molecular mass of hydrated is 152 plus X18. X18. Why is it 18? H2O have a relative molecular mass of, this is 1 times 2 plus 16. That is 18. So that is it. Yeah. So now, what is the mass concentration of the hydrated? Hydrated there is 27.52. 27.52. This is equals to relative molecular mass of anhydrous, which is 152, only this side, anhydrous, only this side, no water of crystallization. Hydrated contains this water, so I'm looking for this alone, which is 152. 152 over the mass concentration of that is 15.5. 15.5. Okay. Now, I'm cross multiplying. I want to make X a subject, okay? So I have my 15 open bracket 152 plus X18 close is equals to 27.52 times 152. So I'm going to expand 15 times 152, 2280. Here is 2280 plus this is 15.5, sorry. Not 15. This times this is 15.5. 15.5. So 15.5 times 152 is 2356. 2356 plus 15.5 times 18. 15.5 times 18 is equals to 279. 279x is equals to 27.52 times 152 is equals to 4183. 18304. Okay, let me take this out. Over here. Now I want to make this the subject. So I have 279x is equals to 418304. 4183.04 minus 2356. 2356. Now, 279x is equals to 4183 minus 2356. 2356. That is 1827. 1827.04. Now, x is equals to 1827.04 divided by 279. And my x is equals to divided by 279 equals to 6.5. 6.5, which is approximately 7. So my x is 7. So the number of moles of water of crystallization is 7, which means this is iron 2 tetraoxosulfate 6 heptahydrate. If I were to replace that. So we've gotten that. No, like I said, the question is not a direct question. You have to solve other things to get to where you're looking for, where you're going to. So we must have to tread with caution in order not to make mistakes. Now let's take, we've just gotten a number of moles of water of crystallization. Now let's calculate the percentage of water of crystallization. Now, percentage of water of crystallization. Let me clean the board so that I'll get it right. Now, this is water of crystallization. To get a percentage of this, it is this, which is the water, all over the total compound times 100. So now I have my percentage of water of crystallization. Water of crystallization, because, okay, of crystallization is equals to X water over F2SO4.X water times 100. X water is 7. X, we got our X to be 7. 7 times 18. All over, I think this is 152. 152 plus 718 times 100. Now, I want to break that. Now, let me explain this. The relative molecular mass of this compound is 152. Here is 18, X is 7, 7 times 18. And the same thing happens here, 7 times 18. So I will be having, let me see, when I do that, what am I going to get? 7 times 18 is 126. 126, okay? Now, plus 152 is 278. Now, this divided by this. Again, I say 7 times 18, 126 divided by 278 times 100. 45.3. This is 45.3%. So that's the percentage of water of crystallization under redox. Now, the last question will be taken as an assignment. We should calculate the percentage of iron 2 in iron 2 heptahydrate. So, this is iron 2 heptahydrate, SO4.7H2O. So this is what we got, as our X, the number of moles of water crystallization is 7. So they have replaced it and knew that it's going to be 7, even when we haven't calculated it. So then they are asking you for the percentage of iron in this whole compound. Remember, when we're looking for the percentage of water, we took water over the total compound. So when you're looking for this, what do? So that's our assignment to that end. So we're going to take our next question, which is question number 3. Let's see if we have more. Okay. Let me take out this. So question 3 says 0.019 potassium heptazodichromate 7 react with 6.0 GDM cube of impure ethane diode acid solution. So this time around we're dealing with percentage purity. You see that we can use redox to calculate anything we want. That's what we're saying right now. 25 cm cube of ethane diode acid react with 23.50 cm cube of KMnO4. If the equation of reaction is given to be whatever it is here, we should calculate the percentage impurity of ethane diode acid. So that's a direct kind of question, but we need to do 1 or 2 conversions to get there. So let's take the given. I have my KMnO4 here. So let's say 0.019 mole per dm cube of this. So the volume, the concentration of oxidizing agent is 0.019 mole per dm cube. React with 6 grams of ethane diode acid. So we have our H2C2O4. The GDM cube of impure ethane diode acid is 6.0 GDM cube. 0 GD of impure ethane diode acid solution. 25 of ethane diode acid, which is the volume. Volume of the reducing agent is 25 cm cube. Of ethane diode acid react with 23.5. Volume of the oxidizing agent is 23.5 cm cube. Or this. If the equation of reaction is given to be this, so for the equation of reaction, we'll be able to get the number of moles of oxidizing agent, number of moles of reducing agent. So let's get the equation of reaction, which is 2MnO4 minus plus 5C2O4, 2 minus, plus 4 hydrogen plus gives us 2Mn, 2 plus 10 CO2 plus 8 moles of water. Remember, this redox equation, we treated it in a particular topic here, part 1 and 2 of balancing of redox equation. So I do not need to start balancing it. It's going to take my time. I just have to balance it before coming here so that I'll just be quick. So if in case you do not know how to balance this, go back to that video of ours, which is balancing of redox equation, and study it. I have part 1 and 2 for this. So you're going to cover all the areas required, okay? So now from here, the number of moles of the oxidizing agent is 2. Here, that of reducing agent is 5. So we'll have that. So now I can claim so that I can attend to other questions. Now, having said that, we should calculate the percentage impurity of ethane diode acid. Now, percentage impurity. We have the mass term. Remember, percentage impurity, we start with percentage purity, which is the mass term of pure over impure times 100. And percentage purity plus percentage impurity is equals to 100. So if we have gotten the percentage purity, we insert it into the second formula, which is percentage purity plus impurity equals to 100, and make impurity the subject. So first, we have to get our percentage impurity that will be able to apply the formula, the formula to get what we want. But before we get the percentage purity, we need the concentration of the reducing agent, which will help us to get the mass count of the pure ethane diol, because what we have is impure. Without that, we ain't going nowhere, so we have to put that down. So now, I will have to put it this way, that the concentration of the reducing agent is what we should look for first. So, it's kind of complicated. You have to get one thing, then go get another, then move straight to what they're asking you. But you have to pay attention to that. If you know all the formulas, you know how to apply them simultaneously. So let's see how we get the concentration of the reducing agent, which will help us to get the mass count of the pure. So for us to do that, remember our formula again: concentration of oxidizing agent times volume of oxidizing agent equals to concentration of reducing agent times volume of reducing agent is equals to number of moles of oxidizing agent over number of moles of reducing agent. So I'm calculating concentration of the reducing agent. So my concentration of the reducing agent will be concentration of oxidizing agent times volume of oxidizing agent times number of moles of reducing agent over volume of reducing agent times number of moles of oxidizing agent. So this is equals to concentration of oxidizing agent 0.019 mole per dm cube times volume of oxidizing agent is 23.5 cm cube times number of moles of reducing agent is 5, all over volume of reducing agent, volume of reducing agent is 25 cm cube times number of moles of oxidizing agent is 2. Okay. So if this is what it is, then this is all equals to this. So we have a 0.019 times 23.5, okay, times 5 divided by 50, 0.0447. This is 0.0447 mole per dm cube. So concentration of the reducing agent now is 0.0447 mole per dm cube. Now we've gotten our molar concentration. So now to get the mass count of the pure, which is supposedly supposed to be lower than this. So let's see how we're going to do that. Mass count of the pure, that one is impure, ethane diol, so we'll look for that of pure. So mass count of pure H2C2O4 is equal to molar count times relative molecular mass of that. So the molar count is 0.0447 mole per dm cube times the relative molecular mass of this. Hydrogen is 1 times 2, which is 2, plus carbon is 12 times 2, 24, plus 16 times 4, which is 64 G mole. So this is equal to 0.0447 mole per dm cube times 90 G mole. So let's see what we have. 0.04465 times 90 is 4.0185. 4.0185, or 3 significant figure 4.01 or 4.02. Let's just leave it approximately 02 GDMQ of pure ethane dioxide. So now I have my GDMQ of pure to be 4.02 GDMQ. Now, what is the percentage purity first? Then we'll get the impurity. Now, percentage purity equals to mass of pure. So let me just call it pure over impure times 100. Mass count of pure is 4.02 GDMQ. Mass count of impure is 6.0 GDMQ times 100. And this is 4.02 divided by 6 times 100 is 67. So this is 67% of pure ethane dioxide. Okay, so if that is 67, they are asking us of the percentage impurity. Therefore, our last formula, remember this is 67, let's not forget that. 67% of percentage purity. So what is percentage impurity? That's the question. Now, percentage impurity plus percentage purity is equal to 100. Now, percentage impurity plus 67 is equal to 100. Therefore, percentage impurity is equal to 100 minus 67, which is equal to. So this is 100 minus 67, which is 33. So this is 33% impurity. So the level of impurity is 33%. So the purity rate was very high. Let's put it that way. So we're going to take, let's call it a last, supposedly. Okay, I have 2 more questions. The last one should be taken as an assignment, but let's take this one. Question 4. So let me clean it up. The question says, if KMNO4 of solution O, so this is my solution, is O, is called KMNO4. O phosphorylation agent, I suppose. React with 0.1 mole per dm cube iron 2 ammonium sulfate has a hybrid as solution R. This is R to be NH4, okay, SO, okay, SO4 dot iron 2 sulfate dot 6 moles of water as R. So R for reducing agent, suppose. And they say the concentration of that is 0.1 mole. So I have concentration of the reducing agent to be 0.1 mole per dm cube. Okay, we have 0.1 mole of iron 2 ammonium sulfate as solution R, and 25 cm cube of R. Volume of reducing agent is 25 cm cube. R gives 24.50 of O. Volume of oxidizing agent is 24.550 of cm cube of the oxidizing agent. If the equation of reaction is this, so we'll be able to get the number of moles of oxidizing agent, number of moles of reducing agent. From the equation of reaction, I have my usual Mn O4 minus plus 5 iron 3 plus 8 hydrogen plus gives us Mn 2 plus 5 iron 3 plus 1 mole of water. So from here, oxidizing agent is 1, reducing agent is 5. Also, one can ask you, okay, let me not go further. There are other questions here we're going to attend to. So let me take this out. We've got to this. Now, they say calculate molar concentration of the oxidizing agent. Concentration of oxidizing agent, molar con. We don't know. That's what they say first. We should calculate. So to do that, we have our formula: concentration of oxidizing agent, volume of oxidizing agent, concentration of reducing agent, volume of reducing agent is equals to number of moles of oxidizing agent and number of moles of reducing agent. This is concentration of oxidizing agent. Oxidizing agent is equals to concentration of reducing agent times volume of reducing agent times number of moles of oxidizing agent over volume of oxidizing agent times number of moles of reducing agent. Okay, this is equal to concentration of reducing agent is 0.1 mole per dm cubed. Volume of reducing agent is 25 cm cubed. Number of moles of oxidizing agent, 1. Volume of oxidizing agent is 24.5 cm cubed. Number of moles of reducing agent is 5. This is equals to. So let's begin. 0.1 times 25 equals to this, divided by 24.5 divided by 5. 0.0204. 0.0204 mole per dm cubed. Okay, now this is 0.0204 mole per dm cubed. Okay, let's proceed. Next question. The mass comm of oxidizing agent. So covering that, let's see the mass comm. Mass comm of oxidizing agent, the GDMQ of this. Mass comm of O is equals to the molar comm of O times the relative molecular mass of O. Now, the molar comm is 0.0204 mole per dm cube times the relative molecular mass of KNNO4. Let me see if it's given. If it's not, then we have to find it. Manganese is 55. Potassium is 39. So let's go. 0.0204 mole per dm cube times 39 plus 55 for this, plus oxygen times this is 64. 39 plus 55 plus 64 is 158. 158 G mole. .0204 mole per dm cube. And this is equals to 158 times 0.0204 is, okay, 3.22. 3.22 GDN cube. Okay, now I come here, I have 3.22 GDN cube of the oxidizing agent. Next question, it says the mass count of R. The mass count of R. Okay, assignment. Then amount of R in one volume of R used. Okay, the C is an assignment. It says the mass count of R. Now, what is mass concentration? The molar count times relative molecular mass. So you're going to calculate the relative molecular mass of this times the molar count of this, and you get your answer. Probably I've told you everything. The D, say amount of R. So let me clean the board and get our amount. So the D amount of R is equals to molar count of R times volume. Volume in dm3. The molar count of R is 0.1 mole per dm3. The volume is 25 over 1000. I'm converting it to dm3. And this is 0.1 mole per dm3 times 0.25, whatever. 25 divided by 1000. So, yeah, 0.025. 0.25 dm3. Now, this is equals to that times 0.1. 0.1 is 2.5. 2.5 times 10 raised power minus 3 mole. The unit is in mole. So, let's take our last question for the day. Let me clean the board. The last question, which is going to be our assignment, so I'm going to read it carefully so we pay attention so we don't make mistakes. Sodium triazosulfate 4 is put in the burette and a known volume of iodine is prepared into the conical flask. Remember, iodine is the oxidizing agent here. But it is prepared into the conical flask and starch solution is used as indicator. If the end point of the reaction is 24 cm cube, so, okay, which is the volume of the reducing agent is the end point because that's what is in the burette. While the concentration of the arrow point A, that is the reducing agent, is 0.100 mole per dm cube. So let me just state them out. So I have sodium triisosulfate 4. Okay, let me just give us our equation of reaction first. We have the oxidizing agent, we have our reducing agent, but our equation of reaction is 2S2O3 2 minus plus iodine gives us X2O6 2 minus plus 2 iodine negative. Now we have the oxidizing and the reducing agent. Let's get it. Sodium triisosulfate 4 is the reducing agent. Is the reducing agent. Is put in the burette, and a known volume of iodine is prepared into the conical flask. Iodine is the oxidizing agent. So since it is the one that is being prepared into the conical flask, the volume of the oxidizing agent here is always 25 cm3. And the volume of the reducing agent is, they gave it to us to be somewhere 24 cm3. That's the end point. They didn't state it clearly. The number of moles of oxidizing agent, this is our oxidizing agent. This is our reducing agent. The number of moles of this is 1. That of number of moles of reducing agent here is 2. Okay, let me see if I've given you everything. If the endpoint of the reaction is 24, while the concentration of the reducing agent is 0.1, reducing agent, the concentration is 0.1. Concentration of the reducing agent is 0.1 mole per dm3. Okay. Calculate the concentration of the oxidizing agent. Yeah. The mass count of oxidizing agent. Yeah. So that is your assignment. Let me read it one more time for the sake of reading. Sodium triisosulfate 4 is put in a burette, and a known volume of iodine is prepared into the conical flask, and starch solution is used as indicator. If the endpoint of the reaction is 24 cm3, while the concentration of the reducing agent is 0.1 mole per dm3, calculate the concentration of the oxidizing agent, the mass count of oxidizing agent, and so on. The equation of reaction was given earlier, so I only cleaned part of it. So you can always get it, is there. So I guess strongly we've done justice to what is obtainable in the redox titration calculations. So we can still use our redox to calculate for percentage purity, water of crystallization, amount, mass concentration, molar concentration, whatever it is. But we must get it right that the formula is not the Ca, concentration of the acid, it's concentration of the oxidizing agent. So it's different. Times volume of oxidizing agent over concentration of reducing agent over volume of reducing agent. The second thing goes the number of moles of oxidizing agent to number of moles of reducing agent. So by so doing, we must recognize our oxidizing agent, our reducing agent, and the equation of reaction most often is given. If it is not given, I have treated it in one of my videos. You can go there to study, to refresh your mind. So in case you come across a question that doesn't have equation of reaction, you will know how to balance that. So aside, I don't think there is anything strange or new in the course of what we're doing. But then, I wish you the best. Don't forget to subscribe and press the like button. See you some other time.